Good morning, ladies and gentlemen. My name is Seongbin Ahn. I'm a graduate student in Department of Mechanical Engineering at Hanyang University, Seoul, Korea. My advisor is Professor Simon Song. Today, I'm going to talk about turbulent Taylor-Couette flow over three layers hydrophobic structures and their drag reduction. First, I'd like to talk about necessity of reducing underwater skin friction drag. Friction drag is related to the velocity and distance of the underwater vehicles. Currently, the underwater vehicles have reached the limits of velocity and distance. As shown in the figure on the right, the limit is due to the skin friction drag. Therefore, improvements in velocity and distance are required to reduce surface friction drag. There are three ways to reduce skin friction drag. First is using polymer injection, and second, the method of spur cavitation, and third is the method of surface modification. We have been studying in the field of surface modification. In the field of surface modification, micro or nanostructure can reduce friction drag. At high Reynolds number, drag reduction is reduced. We have to try to increase drag reduction even at high Reynolds number. For skin friction drag reduction using surface modification, we developed three layered hydrophobic structures. The three layered hydrophobic structures is hierarchical structure. The structure have microstructures and nanostructures and shell coating structures. First, the microstructures can control flow. The microstructures are leaflet and denticle structures designed from shock scales. Second, the nanostructures can trap air. Due to the nanostructures, surface is superhydrophobic. Third, the shell coating improves chemical durability. As shown in the previous slide, the three layers hydrophobic structures is hierarchical structures. As shown in the figure on the left, there are shell-coated nanostructures on the microstructures. The structures is called three layers hydrophobic structures we developed. The objective of this study was evaluation of skin friction drag reduction of three layers hydrophobic structures. There are three detailed objectives. First is fabrication and performance evaluation of three layers hydrophobic structures. And second is visualization of air layers on the three layers hydrophobic structures. And third is friction drag measurement of three layers hydrophobic structures in Taylor-Couette flow. From now, I will explain the method of this study. First, I'd like to talk about fabrication of three layers hydrophobic structures. The microstructures of the structures was fabricated by PDMS molding process. The metal mold with microstructures used for PDMS molding process is made by laser processing. On the flexible PDMS substrate, nano and coating structures were fabricated with hydrothermal growth of nanowires and subsequent ultra-thin film coating. This figure shows the nanowires and coating structures. We also checked the microstructure and nanostructures by CLSEM and SEM. After fabricating the structures, performance evaluation of 3-layer superhydrophobic structures was performed. The contact angle of the structures was 170 degree, and the sliding angle was less than 1 degree. As shown in the moving figure on the right, the rebounding height was 3.6 times higher than smooth PDMS. This result shows the structures was hydrophobic. We also checked the chemical durability. As shown in the figure, superhydrophobicity was maintained after 5-8% sodium chloride solution 1 month and minus 20 degrees Celsius for 12 hours. After fabrication and performance evaluation, we set up Taylor-Couette flow apparatus for air layer visualization and drag measurements. Left figure shows the hardware and software for the apparatus, and the apparatus consists of motor and the torque sensor and inner and outer cylinder. The temperature is measured in real time by thermocouple and controlled with a constant Reynolds number. Next, I'd like to talk about experimental conditions. There was water between inner and outer cylinder, and the gap between inner and outer cylinder was maintained constant, 2 millimeters and 5 millimeters. And the specimen occupied about 21% of cylinder side area. The following results was calculated with assuming 100% of cylinder side area, just calculation. Reynolds numbers were calculated as follows, and the shear Reynolds number and frictional Reynolds number were controlled up to 10,000 and 354 respectively. From now, I will explain the results. First results are visualization of air layers on 3-layer hydrophobic structures. The figure shows the air layer was maintained up to maximum Reynolds number. The presence of the air layer can be seen from no air figure below. The air layer represented follow figures. So the air layer is entirely covered. The second result is friction drag measurements of 3-layer hydrophobic structures. The x-axis represents shear Reynolds number and y-axis represents dimensionless torque. These were calculated as shown on the right. First, as smooth PMMA result shows the blue data, they close to other researchers' results, dotted data. And second, the results of the 3-layer hydrophobic structure, red data, show that the drag is significantly reduced over the entire Reynolds number range. As shown in the previous slide, it can be assumed that the drag is reduced by the air layer. This figure shows the results of other researchers and our result. X-axis represents frictional Reynolds number and y-axis represents percentage of drag reduction. Experiments were carried out on turbulent boundary layer flow and channel flow and Taylor-Couette flow. And microstructures and random nanostructures were used. At high Reynolds number over 300, the drag reduction of the 3-layer hydrophobic structure is significant. We plan to experiment with higher energy number range in the future. Finally, I'd like to summarize this presentation. The objective of this study was evaluation of skin friction drag reduction of 3-layer hydrophobic structures. We fabricated the structures, and the air layer on the structures was maintained up to the maximum main number, and friction drag was reduced by about 29% compared to smooth PMMA at the maximum range number. In the future, we will do air layer imaging and the velocity field measurements of Taylor-Couette flow using PIB. We have been setting up the PIB apparatus, and the cause of the drag reduction will be explained by PIB experiments. I hope to present the results of PIB experiments in the next ASV. This is end of my presentation. Thank you for listening.